Hello and welcome to Analog Electronic Circuits. This is lecture 18 and today we are going to talk about differential amplifiers. We will continue from where we had left in the last class. So, in the last class we were talking about how to analyze the differential amplifier from a brute force point of view, that is by treating the two MOSFETs as a pair of common source and common gate circuits and then doing superposition one by one and finding the result. This is what we were working on in the last class. Okay. So, ordinarily what happens is there is a current source over here, tail current source. This is drawn like this, right. I have unfolded it and drawn it in one vertical column. So, it is the same circuit, it is drawn in a slightly unintuitive way, and when I draw it in that unintuitive way, okay. By the way, this MOSFET, you can think of this as a small signal PMOS also, it makes no difference whatsoever, gate and source, right. It is just the organization of where is the source, where is the gate, that is all. Whether this is NMOS or PMOS, it does not matter. In the ordinary differential amplifier, this is an NMOS device, that is why I have drawn it as an NMOS. But then when I draw it like this, just for drawing sake, it might make more sense to have it as a PMOS, it does not matter. Okay. In either case, what we are going to do is, first we are going to apply V1 and ground V2, measure the two outputs, then we are going to apply V2, ground V1 and measure the two outputs. This is the plan. Okay. So, let us ground V2 and apply V1 and I need to measure the two outputs. This is the objective. Okay. So, now what you have is no, let us do the actually let us do the opposite, let us not do this. Let us apply V2 and ground V1. Okay. The reason why is because in this case it is the second stage is nothing but a common gate, the gate is at ground. All right, fine. So, we are going to apply signal at V2, measure the response over here and then apply signal at V2, measure the response over here. Now, it so happens that just one of these two experiments is enough. Why? Because as you see, the same current flows right through. Okay. So, let us recalibrate our thoughts. So, I am going to apply V2 over here. Think of this as a PMOS if you are not comfortable with this drawing. Okay. I am going to apply V2 signal at the gate. I need to measure the voltage over here and then what is on this side? There is some gigantic resistance on this side, which is a lumped version of whatever you see looking in from the source. All right. So, in other words, we need to do these experiments. We need to, so this is what where we had left off in the last class. We need to figure out what is the impedance looking in at this point, what is the impedance looking over here. We need to also figure out what is this impedance, right, and what is this impedance. All of these we need to figure out. So, let us do it once again. we need to figure out what is the impedance looking in over here. Okay. So, in either case we have to follow the Norton equivalent model, in which case we have to first do the short circuit current, then we have to find out the output impedance, and then we know the different voltages. This is the general plan of the Norton equivalent method. Now, if we want to do that, then I need to find out the impedance looking in over here when V1 and V2 are both at ground. I also have to find out the impedance looking in over here when V1 and V2 are both at ground, and these two are exactly the same. So, just one of the two experiments is sufficient. Okay. So, what is the impedance looking in over here? Looking up I see R, and looking down I am looking down into the drain, right, when the source is terminated with this compound resistor, with this compound impedance. And what is that compound impedance? That compound impedance is also one of the two formulae. So, that is looking in from the source, drain is terminated by R. So, I will see R plus RDS divided by 1 plus GM plus GMB, let us call it GM prime, okay, GM plus GMB. It is just annoying to write that bracket and so on. Okay. So, this is the impedance looking down, and by the way this is the same impedance looking up over here, all right. Then in the next step you are actually looking down from here, right. So, what is the impedance? The impedance is whatever is on the source times the intrinsic gain plus that impedance plus RDS. So, if this is Z, so let us call this Z1, then the impedance Z2 Z1 into the intrinsic gain plus Z1 plus RDS. Okay. So, it is 1 plus GM prime RDS times Z1 plus RDS, which is nothing but plug in, I mean this denominator will nicely cancel out, it becomes R plus 2 times RDS. Okay. Then finally, this is the impedance looking down. There is also an impedance looking up which is equal to R. So, this is what we have computed. Fine. R times R plus 2 RDS divided by R plus 2 RDS. Okay. So, this is the output impedance, and the output impedance is the same looking in from both of the outputs. The output impedance is computed when V1 and V2 are both ground. Now, we are going to do the short circuit current. So, we can do either of the two short circuit currents, and we have to do the short circuit current ideally on both the outputs, but soon you are going to see that it is not required. So, let us work out the short circuit current. When I apply the input over here, and let us measure the current over here. So, when I apply the input over here, what do I do with the other one? The other one has to be grounded. IN is the short circuit current which I need to measure. Okay. What are you going to do first? First what we are going to do is we are going to treat this whole thing as a compound resistor. And we already know its value. Its value is how much? It is Z1 R plus RDS by one plus intrinsic gain. Okay. So, this is some compound resistor, in which case my problem is simplified. My problem actually looks like this. If you are not comfortable with the PMOS, you can always switch to an NMOS, but remember it is terminal for terminal. So, now this compound resistor will still be at the source, okay, and you are trying to measure this current IN. This is something you can do. Is this a problem that you can solve? Should be able to solve this. This is a, what is this? A common drain circuit, right, and the voltage over here. So, the common drain circuit had a gain, the gain was GM divided by, it was smaller than 1, remember, GM plus GMB also came into the picture, plus GDS plus G1, all the non-idealities. Okay. So, that was the voltage over here, and if that is the voltage, that times G1 is IN. Fine. So, this is my short circuit current. IN is equal to GM times G1, where what is G1? G1 is R1, Z1 is this. Okay. So, let us work with it a little bit. Let us modify, for example, let us modify numerator and denominator by Z1 times RDS. GM plus GMB is nothing but GM prime. Okay. And what is this? It is the same thing as before, right? It is GM prime times Z1, GM prime times RDS plus 1 times Z1. Okay, 1 plus GM prime RDS times Z1, where Z1 is this. All right. So, this net denominator is nothing but R plus 2 RDS. You after plugging in the value of Z1. Great. So, what do you have finally? You have IN, this is the short circuit current. Okay. When I have applied V2, the short circuit current is this times V2 is equal to V2 times GM/RDS by so much when I applied V2. Is this okay? So, what all have I done? I have looked at the circuit from this point of view. I applied V2 over here, and then I found the output impedance looking in from this point, and I also found out the short circuit current going into the circuit. Okay, these are the two things I have found out. And therefore, what is the model? The model is that you have got, you apply a V2 and as a result you are going to produce a voltage which is minus of this current times the output impedance. Okay, so, this is the model, this is the Norton equivalent to Thevenin equivalent transformation. Okay. And therefore, what is the voltage over here? The voltage over there is minus of IN times the output impedance. What was the output impedance once again? Okay. So, this was the output impedance, this factor nicely cancels out and I end up with the output voltage to be equal to minus V2 times GM RDS by 2 into R plus RDS. Okay. So, what have I done so far? Let us again recapitulate, because a lot of you are probably feeling a little lost over here. So, that is why I am recapitulating again and again. I have two inputs to this circuit, V1 and V2 ordinarily. Instead of two inputs, I am going to do superposition. So, I am going to do inputs one by one. So, first we connected V1 to ground, and we are now experimenting only by applying V2. Now, when I applied V2, I measured the voltage here and I found that this voltage is minus V2 times GM RDS by 2 R plus RDS. This is what I have found so far. Okay. This is R. So, therefore, what is this current? This current is just this voltage by R, and where is this current coming from? It is coming from the top. So, therefore, what is the voltage here? this is also R. So, once again I have got a voltage V, let us say this voltage is V, forget what its value is. I have a voltage V, this current is V by R, the same current is flowing from the top, that is also V by R, it is dropping across R, and therefore, this voltage is V, and therefore, what is the voltage here? You started from 0, therefore, this is minus V, okay, which means that this is plus V2 times GMRDS by 2 into R plus RTS. Is this okay? Great. Now, what we are going to do is, we are going to apply V1 and ground V2. And when I apply V1 and ground V2, the same thing is going to happen, just that now it is because of V1, and now this node is going to respond with a voltage minus V1 times GMRDS by 2 R plus RTS. And because this node is now minus V1 GMRDS, right. So, now I define this current is going to flow right through over here, and therefore, the voltage over here is going to be plus V1 times GMRDS by 2 into R plus RTS. Okay. Now, I apply superposition and I apply V1 and V2 at the same time. So, now I will have effect of V1 as well as the effect of V2, which is the sum of the two expressions. Alright. So, now my entire problem is solved. So, my entire problem now has, I applied V1 and I applied V2. On one side I got V1 times GMRDS by 2 R plus RDS minus V2 times the same factor. On the other side I got V2 times the factor minus V1 times the same factor. In other words, this was my circuit. When I applied V1 over here and ground over here, I got a response minus of that response. I applied V2 over here, ground over here, I got a response over here and minus of the response over there. Okay. Net superposition is the combination of both. Fine. If I apply V1 minus V2 as my input signal, the signal part of the input is V1 minus V2. The interference part of the input is the average of V1 and V2. Okay, this was the understanding that we had. Now, if you look at each of these individual voltage output voltages, they are proportional to the signal, both of them, right, because these two factors are the same. So, one node is minus V1 minus V2, so minus of V1 minus V2 times GMRDS by 2 R plus RDS. The other one is plus V1 minus V2 times GMRDS by 2 into R plus RDS. If you now look at the difference of the two voltages, right, then that 2 factor will go away. This 2 factor will go away. So, it is now this top one minus the bottom one, right, V1 minus V2 is common, everything else is common. So, the 2 factor will go away, it becomes double, right, the difference becomes double and it becomes the the difference of the two outputs is divided by the difference of the two inputs is nothing but GM RDS by R plus RDS. Is this okay? Do you understand? So, we get exactly the same result as we did in the earlier classes. In the earlier classes, we took a shortcut, we used symmetry in the circuit to come up with the answer. In this, we did not use that shortcut, right. We did a more brute force kind of analysis, but when I do these brute force analysis, I did not really draw the small signal model of the MOSFET. Did I? Did I draw the small signal model of the MOSFET? Never, right. The small signal model of the MOSFET was not even required, right. I avoided it altogether, right. I did not expand the small signal model of the MOSFET at all. So, do not when you try to analyze something by brute force, even brute force can be smart. It is not like you immediately split up the MOSFET into GM, GMB, RDS and then start solving the circuit. No, that is not what we are going to do. We are going to look at impedances, right. We are going to look at impedances. What is the impedance looking in from the drain? What is the impedance looking in from the source? And accordingly, we are going to analyze the circuit. For example, suppose this current source was not ideal. What would you have done? Now, the general idea would be, once again you are going to do both short circuit current as well as output impedance, right. That is the general idea. Now, when you are doing output impedance, you look up, you will see R, you look down into the drain, right. You see that the source is terminated by some impedance. What is the source terminated by? On one side it is terminated by the impedance of the current source, on the other side it is terminated by whatever is looking up into the source. So, you put these two in parallel, right, combine them. Now, that is what is terminating the source. Now, when you look in from the drain, it is 1 plus the intrinsic gain times what is on the source plus RDS, okay. And that whole thing is now the output impedance looking in from a node, right. Is that okay? That is how you are going to analyze it. You are still not going to break it up into the small signal models of the individual MOSFETs. Okay. Then in the next step, you are going to say, okay, now what is the short circuit current? So, you are going to apply V2 over here and then measure the current in this. How do you measure the current? First, you are going to apply V2 and then you are going to lump all of this as one resistor, and we already know how to lump all of this as one resistor. It is this resistance, equivalent resistance in shunt with the resistance looking into the source. We know how to do that. So, it is now lumped, and therefore, now I know the voltage over here because this is a simple common drain circuit. If I know the voltage over here, then I know the current, that is the short circuit current. Okay? You see the line of thought? We are not going to break it up into the small signal models at all, right. These, now there could be mismatch. These two MOSFETs could have been different, that is okay. These two resistors could have been different, that is also okay, right. Nothing is going to bother you because you are going to do it step by step. First, you are going to find out the short circuit current over the output impedance over here, then the short circuit current over here. That will tell you what is the voltage over here when I applied V2 and grounded V1. Okay. Now that you know the voltage over here, now you know the current, the same current is going to flow. Now, you know the voltage here as well. So, you have two output voltages, one over here when you applied V2. Okay, and we did not worry about symmetry. In fact, the circuit could be totally asymmetric. These two MOSFETs need not be ideal, equal. These two resistors need not be equal. This current source need not be an ideal current source. The technique remains exactly the same. Do you understand this? Okay. because sometimes when there is imbalance, this might be the easiest way to proceed forward. Okay. Suppose these two MOSFETs are so different that one is a MOSFET, the other is not even a MOSFET, it is a BJT. Will you be able to solve this? You should be able to solve it, because nothing much has changed. Okay. You are doing exactly the same technique over and over again. You are always trying to find out impedance levels. According to impedance levels, you are going to work out the currents and proceed forward. All right. Now, next what we are going to do is, we are going to talk about this resistor. So, we have seen this before, that this resistor is an irritant. It is a very annoying piece over there. Why is it annoying? Because the value of that resistor should be as large as possible. Okay. The largest possible value is infinity, which means that resistor becomes an open circuit. But if you have an open circuit there, then the rest of the circuit does not work, because you do not get a GM on the MOSFET. Okay. So, that resistor is rather irritating, because for DC conditions you want a certain current to flow through that resistor, but for AC conditions you would rather have an infinite value. Okay. For the signal you would like to have a very large value for that resistor, right. So, it is a little annoying. How do we proceed? So, this resistor creates swing problems, right. I mean you try to trade off. On one side you have to have reasonable swing, on the other side you have to have bias current, on the other hand you have to have gain in the amplifier, right. So, all of these will conflict with each other. You will not be able to find a reasonable value for the resistor given all your specifications of the gain as well as the swing as well as the current and so on and so forth. So, this resistor is rather annoying. Any way to replace this resistor? So, what property do we want? As far as DC goes, operating point goes, we want current going through the resistor. Okay. But as far as signal goes, the higher the value of resistance, the better for us, because then we will get more gain. Okay. So, this is what we need for that resistor over there. What can we do about the resistor? What is it that you want to do? You want to replace it with an inductor? Okay, inductor is not a bad idea. If you replace this resistor with an inductor, then as far as DC operating point goes, it can carry any current that you want, right. The inductor is a short circuit. Okay. But for signal, which is AC, the inductor effective value is j omega L, which is a very large impedance. You pick your L value as large as possible and you will be fine. Okay. So, this is certainly a solution, it is a valid solution. A lot of RF circuits you use this technique, because in RF the value of omega is large, and when the value of omega is large, you do not need very large values of inductance to achieve the desired response, right, j omega L. is the impedance for the signal, right, where omega is the frequency of the signal. Now, at very large omegas, you do not need a gigantic value of L. However, if you are not, if your omega is not very large, if your omega is 1 kilohertz, 1 kiloradians per second, then you need a very large value of L going even into all the way into henries, right, and that will make the inductor very big and bulky, okay, and in such a case it is not a good idea. So, this is a solution, it is a valid solution, replace the resistor with an inductor. It is a valid solution when we go for RF circuits, that is at very high frequencies. At very high frequencies you do not need large values of inductors. So, for example, gigaradians per second, okay, tens of gigaradians per second, hundreds of gigaradians per second. In such a scenario, let us say you want 10 kilo ohms over there, right, 10 kilo ohms, and you have your omega is 10 gigaradians per second. The Z value you require is 10 kilo ohms. In that case, the L value 1 nanohenry is sufficient. Is that okay? 1 nanohenry? No. 1 picohenry. So, 10 gigaradians per second j omega L, forget the j part, 10 kilo ohms. So, L is 10 k by 10 giga, the 10s cancel out, kilo by giga is how much? Kilo by giga is 1 by mega, so 1 microhenry. Okay. So, 1 microhenry over there will be sufficient to give you 10 kilo ohms of resistance. Okay, 1 microhenry is a little too much, but 10 nanohenries is reasonably small that we normally go ahead and implement, in which case you do not get 10 k, you only get 100 ohms. Okay, but that is a solution that is workable. This is something that is workable at very high frequencies. At low frequencies this is not workable because the inductor value becomes so large that it is not, it becomes big and bulky. So, it is not a workable solution at low frequencies. So, what do? We still have the problem. We need to replace this resistor by something a little smarter. For operating point I need to conduct current, but for the signal I need a large value of impedance over there. What is the answer? Yeah, inductor is done. Inductor works for RF. What else? Any other solution? A current source. Great. So, a current source will work. So, something like this. Okay. This current source at DC it pushes a certain amount of current, which is the bias current required for the device, but for signal, as far as signal is concerned, this current source is going to behave like a large resistor, and that is perfect. Okay. The larger the resistor, the better, the more ideal the current source, the better, because then the output impedance on the top side. So, if you look at the output impedance looking in from the node, you have on the top side you have very high impedance of the current source, on the bottom side you have RDS. So, your net output impedance is RDS, and therefore, the gain is going to be minus GM times RDS. Okay. So, this is the general strategy. This is a strategy that we are going to use. So, instead of a resistor, we are going to use a current source. How will you make a current source? How will you make a current source? With a current mirror. Okay, what's inside a current mirror? A MOSFET. Okay. So, let us think of this as our common source amplifier. Instead of having an R on top, let us have this structure on top. Once again, this is the small signal incremental picture I have drawn. I have not drawn the entire circuit. Okay, we will draw the entire circuit. Let us first see if this small signal incremental picture is good enough for us. Okay. So, what is the short circuit current? If I connect this to the output straight away, what is inside this MOSFET? Inside this MOSFET there is RDS and there is a GM, but the GM does not matter because gate and source are both at ground. So, VGS is ground. So, this MOSFET only has RDS, okay, to ground. Now, I put a short circuit to ground, that means that RDS to ground is now irrelevant. This MOSFET also has RDS to ground and that is also irrelevant. This MOSFET has GM because VGS is the input voltage. So, it conducts a current GM times VGS and this entire GM times VGS is going to come right through the short circuit. All right, that is the short circuit current experiment. The second experiment is the output impedance. Now, when you look at the output impedance, you look in from outside, you can look up, you see RDS, you look down, you see RDS. So, net effect is going to be RDS1 in parallel with RDS2, and therefore, the gain of the circuit is going to be, oh, you are not happy with the gain of the circuit, is it? Okay. So, we do this Norton equivalent model by computing the short circuit current and the output impedance, and then in the next step, if you want a voltage gain, then you convert the Norton equivalent into a Thevenin equivalent. And the way we do that, one easy way to do that is to imagine the Norton equivalent model and just see what is the voltage that you get. This is the Norton equivalent model. This is what you have modeled. Okay, here this current is GM1 times V in. This impedance is RDS1 in parallel with RDS2. What is the voltage over here? Yeah, forget the load, there is no load over here. We are trying to find the voltage gain. If you want to place a load, go ahead, place a load, that will change the voltage gain. Right now, it is going to be RDS1 parallel with RDS2 in parallel with the load, that is okay. So, it is going to be the product of the transconductance GM1 and the output impedance. So, the product of the transconductance and the output impedance with the appropriate sign is going to be voltage gain. Appropriate sign, this sign could be positive or negative depending on the direction of this short circuit current. Transconductance times output impedance. So, that is the voltage gain, okay, short circuit transconductance. All right. So, here the voltage gain is minus GM1 RDS1 in parallel with RDS2. Okay. So, this is going to be our plan. instead of having RDS1 in parallel with R, I am going to have RDS1 in parallel with RDS2. This is nicer because R has limited values possible, right. When I increase R, for example, the current decreases. If I decrease the current, then GM changes, all kinds of funny things happen, they are all interrelated. So, let us not worry about R, let us throw out R, let us replace it with a current source, right, or in other words, let us replace it with a MOSFET, in which case my gain becomes minus GM1 RDS1 parallel RDS2. Both RDS1 and RDS2 are comparable to each other, these are similar in terms of value, hopefully. All right. So, therefore, this is a small signal diagram that we want. This is the small signal incremental circuit that we want. If this is the small signal incremental circuit, what is the full circuit? So, let us go back a few steps, let us think of the common source amplifier and then we will change it to the differential amplifier. So, for the common source amplifier, we applied the input over here. I did not know the bias voltage of the input. Okay. I have to work out the bias voltage. Input is coupled onto the over there, and then I have to work out the bias voltage at the gate of this MOSFET, that is also something I have to work out. So, let us say I have a current reference. So, I pull this current through this MOSFET, this is the desired drain current of the MOSFET to give me the right amount of GM of this particular MOSFET. Okay. This is the current mirror. Now, I also have to create the right bias voltage here. So, maybe what we can do is we can have it set up like this. Is this okay? Yeah, I have thrown out the source degeneration, all of that has been thrown out. Let us say I work out what is the right current that I need to achieve a certain GM. I make that current source. Now, I use that current source to work out what is the right value of the gate for the PMOS. I use the current source to work out what is the right value at the gate of the NMOS and bias them. Is this okay? This is the overall plan. Okay. This would be a good plan for the single ended structure. Now, yeah, so this floating current source is a problem. We have not really learnt how to make a floating current source. We have current sources so far we have are all terminated on one side to ground, but that is okay, you can make a copy of the current and then copy it again. So, for example, you could do this. So, this is your final device, and then in the interim you can create another copy of it. Is this better? Do you like this more? There is one more job that needs to be done. there is one more job that needs to be done, and that is to isolate the signal from the bias, and to do that we have to place a large resistor in this path. Okay, so that the signal does not go inside the bias, otherwise the signal goes inside the bias and starts waving around this current or this voltage over here. That should not happen. So, you place a large resistor over there, so that the signal does not leak into the bias side. Okay. Here as well. Is this okay? Rest of it is good? All right. So, this would be a nice amplifier, right. So, we have completely gotten rid of all those bias resistors, right. Earlier we had 4 bias resistors, RD, RS, RD was also the load, right, RS, then R1, R2, all of those are gone. We have just one resistor over here of arbitrarily large value, okay. Otherwise it is all MOSFETs. You create the current such that the GM is good, and then you mirror that current, create copies of the current, right. Why is this good? You are using so many devices, so many MOSFETs. Earlier you had one MOSFET, now you have 1, 2, 3, 4, 5 MOSFETs plus what is inside the current source, another 4 MOSFETs inside the current source, 5 MOSFETs inside the current source. So, 5 plus 5, 10 MOSFETs. Is this good? The thing is that this is great, it is not just good, this is great. Why? Because you could throw out resistors, and on an integrated circuit resistors are no good, just not good. Okay. MOSFETs are fantastic on an integrated circuit, they are easy to make, they require less steps, they are reliable, they have all the good properties. A resistor means an extra mask, it means extra cost, it is gigantic, its resistivity is not very large, so it is going to be big. All kinds of problems are associated with resistors. If it is possible to avoid a resistor, then please avoid the resistor. So, this is actually great. The next thing is, in this the value of GM is controlled with the help of this current source. Okay. In the earlier design the value of GM was uncontrolled, right. So, the entire structure is much nicer in this particular case. All right. Now, what do we do in case of the differential amplifier? So, the differential amplifier, we are just going to replace the resistors on top with MOSFETs. That is it, right. The rest of the stuff remains exactly the same. Bias voltages of these two nodes are not a worry. Why not? We discussed this. They are not a worry as long as they are such that this current source remains in saturation. Okay, it is dictated by the bias voltages over here are dictated by the current. Okay. So, whatever the bias voltage here is, the bias voltage here is going to be VGST plus VT less than the bias voltage at the gate. Bias voltage at the source, operating point voltage at the source is VGST plus VT less than the operating point voltage at the gate, and that is okay because this is a current source. Okay, that is perfectly fine. So, the exact DC operating point voltages at the gate are not really very important, it can, as long as it is above a certain value. Okay. Now, what about these PMOSs? These PMOSs need to conduct a certain amount of current, in which case we have to mirror just the right amount of current, and what is, if this current source is I naught, then each of these have to be I naught by 2. Okay, so it is a current mirroring exercise. Let us say I have a reference current I naught, and then in the ratio 2:1, I need to create I naught by 2 in each of these. Okay, and then I have to create this also. So, from the same reference current, I will create one more copy, and then copy it again. Okay, so it is now a copy of a copy. So, a structure like this is the general plan. Okay. This is the overall differential amplifier now, right. No resistors, only MOSFETs, right. All the bias voltages are taken care of with the help of current biasing. We are now biasing with the help of a current source and current mirrors. Now, what is the value of this current source? This value of this current source is going to come from some constant GM biasing circuit. Again, 4 MOSFETs, 1 resistor. Remember, we discussed that. Okay. So, the entire structure is now current biased, not biased with voltages anymore, they are biased with values of currents. The operating point is set by currents. Okay. So, let us stop here. This is basically the overall discussion of differential amplifiers, right. We have to do one more very important differential amplifier structure. This kind of a differential amplifier is called an active load. The load of the differential amplifier is active. Almost all differential amplifiers today are active load. So, the next what we are going to do is we are going to do a self biased active load differential amplifier, and that will close this particular topic. Okay, thank you.